The purpose of end-to-end security is to reduce the number of parties the users are required to trust. Proprietary messaging products make use of end-to-end cryptography, but fail to achieve that purpose. End-to-end means nothing if users are required to trust the sole source provider to identify those ends. Our next talk is about the mathematical mesh, a personal PKI addressing their trust gap. We present Philip Hallam-Baker with Beyond End-to-End.
So here we are. Can't attend our hacker convention because of the plague. Hello, I'm Philip Hallam-Baker, and at the beginning of this presentation, I want to explain why this end-to-end security we've been hearing so much about for the past 3 decades isn't actually what we need. And at the end of the presentation, I'm going to be announcing the mathematical mesh, a free open source infrastructure that makes end-to-end security practical and usable. So in between, I'm going to be explaining what we really need, how end-to-end isn't quite enough, and how PKI, public key infrastructure, isn't quite enough. We need to go a bit further and start applying a type of cryptography called threshold. And to apply it, we're going to need a threshold key infrastructure, which is what the mesh is. So this is the condensed version of what is a 20-part architectural series of podcasts. So don't worry if you miss any of it. There's also a separate course on threshold cryptography that I'm currently working on that will go into the techniques that I'm glossing over very quickly here, that you can go back to and find out what's going on. So don't worry if you miss it in the condensed version. So here we are, all in our homes, living life by Zoom conference call. And of course, Zoom, it isn't end-to-end secure. The server, it could be in China. Horrors. So, of course, the most important thing to do for security right now is to make Zoom end-to-end secure, isn't it? And to let people choose where their media conferencing server is. That's important, right? Well, no. 3 main reasons. First, security doesn't depend upon geography. China isn't your only security threat. They're not the only country that spy. They're not the only country that spy using computers. Russia also spies using computer. Iran also spies using computers. And they all have hacked servers in the US in recent months. That's just a fact of life. And you know what? There's even rumors that at some point the United States might start doing the same thing. The second reason is that money is the motive. Yes, if you're a dissident, a hostile authoritarian government, and hey, there are a lot of those around now, is a significant threat actor. But for most people, most of the time, the threat actor of concern is attackers that are looking to steal money. And that's even the case with most Chinese espionage. Most of it is commercial espionage, and most of it is actually targeting other Chinese companies. The reason they have difficulty understanding our complaints is that's just the way they do business over there. Everybody's spying on everybody else. Sales data, trade secrets, any knowledge that can give an insider trader an edge. That's the target. And that brings us to reason 3. Information is the target, not your Zoom call. The attackers don't care whether they get your data from a Zoom call or from an Excel spreadsheet. But, you know, if they're attacking somewhere, it's a lot easier to pick up interesting, valuable data from a directory with 1,000 Excel spreadsheets than one with 1,000 saved Zoom conference calls. And intercepting that Zoom conference call, harder still. So the reason that I talk about Amazon Cloud Services being the Fort Knox of information security isn't that I'm terrifically impressed by their security. It's because they create a Fort Knox-sized breach initiative. Amazon Cloud Services is where the data is. And in our economy, information is worth more than gold. It's hard to secure. You don't know when somebody's stolen it. So all this fuss about Zoom, they're just the latest hole in the fence. And that's the reason that people are worried about it, because they hadn't noticed there was a hole there. But yeah, how many Zoom conference calls do you have in a day? How many of those have confidential information? How many emails do you send and receive every day? How many of those have confidential information? And do you encrypt your sensitive documents? Well, maybe you might, but if you do, chances are you encrypt them under a password and then send the password along with the file that was encrypted.
In the VCR!
And, well, that's probably true even though this is a hacker conference. At any other conference, everybody would be nodding and saying, yeah, we do that. And of course, that's exactly how these Zoom end-to-end secure conference credentials are going to be passed out in email along with the conference call number.
In the VCR!
So Zoom isn't really our biggest problem, but if we're going to secure anything, we've got to have a plan to secure everything. If we just go after things piecemeal, we're just going to be stuck in the same situation in 10 years' time that we're in today, which is nothing is really particularly secure and everybody just gets used to that fact, like we have with email. So we don't have to solve every problem immediately. Zoom ain't the top of my priority list, but we need an infrastructure that can provide security to any application that we need to apply it to, and especially new applications that people haven't yet become complacent about. And one of the reasons for that, of course, is that security only works when it's being used. I mean, PGP and SMIME now have been around for over 29 years. I was just looking it up. SMTP email is about 40 years old. PGP about 30 years old. So, secure end-to-end mail has been in existence for 75% of the life of SMTP, but nobody uses it. There are about, there are a few million PGP keys on the public servers. Well, there are a few billion users of email. If PGP and SMIME haven't got to critical mass yet, they're never going to do that. And the reason is simple. It's too much effort for the users. And for most users, any effort is too much effort. This is why, security usability, testing stuff in labs, no, you don't need to do any of that. If you require your users to do anything different, you're doing it wrong. But trying to configure PGP or SMIME is like having somebody pull your toenails out. It really is a painful experience, and especially if you're trying to use it across multiple devices. And the reason for that is that we don't have an infrastructure for managing private keys. And this is one of the problems with end-to-end security, because in every case, the endpoints in a cryptographic end-to-end secure system are cryptographic keys, not devices, not people, keys. So if you don't have a way of being able to securely transfer those keys between the user's devices, you've not got a system that's not going to work for them. Okay, so it's not working today. What does work? Well, one thing that does work is reducing the number of trusted parties. If you have to trust 5 people, you're a lot better off than if you have to trust 500. And this is what end-to-end security is about on the internet. It's a means, not an end. The end of end-to-end is to reduce the number of trusted parties, so that you only need to trust the endpoints of the communication and not every ISP that the data happened to have passed through. Same thing with login screens, if you think about it. If you have a machine without a login screen, anybody who passes by can go go up to that computer and mess with it. And we used to see a lot of that in the MS-DOS days and the original Mac-OS days. Once you have account-based security on that machine, even if it's not perfect, you're limiting the number of people you can trust to the people with a username and password and the people who know how to get around them. But reducing the number of people you trust, it's been the obsession of many people for the past 20 odd years. That's not enough. What is even more important is reducing the extent to which you must trust a particular party. And this is actually what industrial scale PKI is all about. It's all about separation of roles, separation of duties, so that there isn't a single employee who can get hold of that root of root keys and do terrible things with it. And so reducing the separation of roles is the principle for high security, but that's not where the corporate vision is right now. The corporate vision is very clear. And anybody who remembers David Chaum's keynote at the first World Wide Web conference will be getting a sense of deja vu at this point, because what David Chaum said about interactive TV is exactly the same as what's currently happening with secure end-to-end secure messaging. The corporate vision is very clear. Microsoft wants you to trust Microsoft Skype running under Microsoft Windows on a Microsoft Surface tablet, and it's all going to be protected by Microsoft Windows Defender. Apple's got a completely different vision. Their vision is you're going to trust Apple FaceTime running under iOS on an iPad. But that's not the case for Google. Their vision, well, they've not quite got to a vision yet, but just you wait. Google is going to buy either Signal or Zoom, and then you can run that on your Chromebook. So what they're looking for is this corporate monoculture of trust me absolutely, and that should be something that gives everybody cause to run for the kills. Not just the people who are being asked to be customers, the corporations that are proposing this preposterous thing. Just think of the steaming piles of liability you are storing up there. Because if you make people absolutely rely on you, then if there is a problem, they're going to come to you as the only person who could have caused it. And maybe if there wasn't even a problem, maybe if just somebody said there was a problem, you don't need to be breached to be blamed. Just ask Hillary Clinton. And the effect of a possible breach these days is pretty much the same as an actual one. There are many companies that have spent millions resolving data breaches where they weren't sure they were breached. All that happened was that their information was exposed, so it might have been. But they still have to spend that $30 a time sending out all those letters to tell people they may have been breached, etc. So what we need here is to take separation of roles seriously. And this is what we did at VeriSign. Nobody had access to all the key shares required to enable one of the roots or any one of the service keys. Separate roles, separation of duties between hardware and key shareholders and everything. It was all there in the CPS. So what we need to do is to apply this to the emergent end-to-end messaging so that we have separation of roles. At the hardware level and the platform level, it means being able to choose your vendor so that you're not locked into just the messaging or chat that your particular hardware vendor has provided. At the application level, you absolutely need to have the ability to run a different client. If Signal are the only people who are providing the client for the Signal messaging service, well, the FBI can go to them with a warrant and say, either you put this back door into Bongo Phil Baker, or you go to jail. And you know what? I like Moxie, but given a choice between go to jail and put the back door in, how do I know which he will do? And you know what else? They don't just need to go to the CEO. They can go to anybody in the management chain and tell them not to tell the superiors. And we also need to have separation of roles at the service level. We need to be able to mix and match service providers. You're never going to have real security in somebody's walled garden, no matter how much you think you can trust them. You've got to be able to choose your service provider. You've got to be able to communicate with the users of other security service providers. And you've also got to be able to change your service provider if you're not happy with them. If you've not got that, you're stuck into this single stovepipe that is a walking hazard for being lawfully intercepted. So in short, everything that we said in the 1990s when we were building the web about interactive TV is true today of the so-called secure end-to-end messaging. What we need is systems that have separation of roles, separation of functions, and we have a system in which the user is in control, not whoever is running the service and creating the user base. Okay, so this is about, I'm a cryptographer or cryptographic protocol designer. So what does this mean for cryptography? How do we get separation of roles at the cryptographic level? How do we go beyond S-MIME, beyond PGP, beyond even Signal? Okay, well, let's just recap and look and see why public key cryptography was such a revolution. Symmetric key cryptography used the same key to encrypt and decrypt, which meant that anybody who was given the encryption role also had the decryption role. That's why this thing didn't work. Every Nazi cipher clerk who had the Enigma cipher wheel settings of the particular day could encrypt or decrypt any message. And that had the side effect, of course, that anybody who'd broken those cipher wheels also had all those messages. So public key cryptography was important because it allowed us to introduce two keys. Separate keys to encrypt and decrypt means that we can have separate roles for encryption and decryption, and granting one role does not necessarily grant the other. Same for signature and verification. Two keys means we can have two roles. 3 keys means we can have 3 roles. 4 keys, 4 roles, and so on. So when we're looking to apply our separation of duties at the cryptographic level, we need to introduce more keys. And public key cryptography only gives us 2, the public key and the private key. If we want to be able to have more control, we've got to be able to start splitting up keys. Okay, how do we do that? Well, there's a simple answer: math. Okay, well, and here it's going to get really hairy. Okay, so the industry standard that we use for public key cryptography today is elliptic curve Diffie-Hellman. An elliptic curve is a mathematical construct called a group, and what we do is that first of all we define an operation we call point addition. It looks nothing like addition. It's drawing a line between points on the curve, but we call it addition. And it turns out that that operation has a property called the group property, which I won't go into here. And having defined this operation point addition allows us to define a second operation, scalar multiplication, in such a way that it's easy to calculate the scalar multiplication of a scalar value by a point on the curve. That is easy. But going the other way, point division, that is not easy. That is an infeasible. So if we have a 448-bit curve, the scalar multiplication will cost us 448 operations. the inverse, the division, will cost us 2 to the power 224 operations. So it's got that cryptographic property of easy to calculate in one way and difficult to go in the other way. Okay, so elliptic curves over a finite field are also a group, and they obey the associative and distributive law. The associative law is what allows elliptic curve Diffie-Hellman to work. What the associative law says is that if we take if A and B are scalars and P is a point, well, we can multiply A times B and then apply that to the point, and we'll get the exact same result as we will get by multiplying B by the point and applying A to it, or applying A to the point and then applying B to that result. So what it says is that we can do these operations in any order and get to the same result. And that's exactly how Diffie-Hellman key agreement is working. The private key in Diffie-Hellman key agreement is a scalar. The public key is simply that scalar multiplied by what we call the base point. Now, one consequence of this system is that we can actually do math on public key pairs. If we have a private key, which we know, which by definition is x plus y, so the private key z equals x plus y, the corresponding public key z dot the base point is going to be the same as x plus y times the base point. Well, that will also be the same as adding the two public keys for x and y. And this is because of a second law that elliptic curves obey called the distributive law. We can add the two scalars together and apply them to the point, or we can apply each of the scalars separately to the points and add the 2 points. We will get to the same result. We can do math on public key pairs. And the operation to find out the new private key, all we need is the private key values. To find out what happens to the public key, all we need are the two public key values. And that allows us to do some really, really interesting things with what's called threshold key generation. Okay, what does this mean in practice? Well, let's say that we ship a machine with today with a private key that's installed during manufacturing. It's going to be welded to the machine like we do with a smart card. It's never going to leave this machine. Well, not unless somebody persuades it with some liquid nitrogen, electron microscope and all that stuff. So the machine has a little code processor that, given a point on the curve, returns the private key multiplied by the point. And this would allow us to do traditional Diffie-Hellman, elliptic curve Diffie-Hellman operations with that CPU that were completely welded to that machine. Well, could we use it? Well, I don't think I'm going to want to choose X, that machine installed in the machine, as my PGP key. I mean, go on. I mean, like, yes, I might trust the Intel CEO, but there's a whole supply chain below him that might have been compromised. Everybody in Intel might be completely trustworthy, but the person who programmed the machine that installs these private key values, X might have created a backdoor and all that sort of stuff. And so, yes, I can trust a manufacturer to provide a private key that ain't going to leave that machine. What I cannot trust them to do is to produce a machine with a private key in it that absolutely nobody else knows. So what I want to be able to do with my threshold key generation is to generate a second key for my application and then join the two keys together and use that composite key with a composite of the two security properties. The application key that I've generated in my application provides me with the security property of secure from Intel or AMD or whoever backdoor. The key that is provided by the manufacturer provides the property welded to this particular CPU. And so threshold key generation allows us to combine private keys and public keys from separate sources and create a composite key which has multiple security properties that are desirable. And yes, we can perform public key, the Diffie-Hellman operations, because the Diffie-Hellman results also obey the distributive law. Second thing that we can do is we can do cloud encryption. And here what we're going to do is we're going to start with a key that is a single private key for the group, and we're going to split it between a user and a cloud server. And there are going to be multiple users, and we can create these splits as users are joined or leave the groups. As many different splits as there are members in the group. And what this allows us to do is to create a cloud service that can control the use of decryption but cannot decrypt. Why is that valuable? Well, read Snowden's book. If you look into how the Snowden breach occurred, it wasn't because the NSA didn't understand cryptography. They do. The problem is they don't know how to apply cryptography in a way that makes the data that they've encrypted usable in their organization. And now this isn't in the book, but I've talked to some folk who know, and they told me my theories that were wrong, which has led me to a 90% confidence, and since I've not got a security clearance I can talk about this, that yes, the documents that Snowden breached were encrypted, and they were secured using the Microsoft CRM server, which is based on the old Ford Wiener key release scheme. And the reason that they were breached was that Snowden had access to the admin keys for the servers in question. So this is the reason why threshold cryptography, threshold encryption and decryption are so interesting, because we give one half of the decryption key to the user, but they've not got absolute ability to decrypt anything they like. We want to have accountability. We want to have attribution. We want to be able to take away their ability to decrypt if we need to. And that's the job of the cloud service, which has the other half of the key and has to be involved each time a document is going to be decrypted. So the user can decrypt, but only with permission of the service. The service cannot decrypt a call, and there's actually an information theoretic proof that we can deliver for that. Again, 40 minutes, I've not got time for it here. So what does this give us? It gives us flexibility. We can grant or remove access to any user at any time, and they've got access to anything that was encrypted under the group key. It gives us accountability, because every access has to go through that server interaction. Well, we can design an authentication scheme with non-repudiation. So now we've got attribution. Attribution plus consequences equals accountability. And we can also apply usage-based access control, which gets us onto the other famous NSA responsibility breach, which is, of course, the Manning breach. Why did Manning have access to 400,000 diplomatic cables? Well, she didn't need all of them, but she needed access to some of them. And the computer system that was controlling them didn't have the capability of working out how much usage a particular user was making use of. So we can use this key server as a control point and put a meter on decryption. Okay, so that's the vision. How do we get there? Well, in order to make effective use of encryption and decryption in Project Athena, MIT had to invent, or rather implement, a symmetric key infrastructure, Kerberos. To make use of public key cryptography in order to send and receive encrypted email in order to enable secure web transactions, we needed a public key infrastructure. Very similar under the covers to the symmetric key infrastructure, but added a few additional functions. If we're going to make effective use of threshold cryptography, we're going to need a threshold key infrastructure. And that is what the job of the mathematical mesh that I've been working on for the past few years is all about. But the mesh is a TKI, a threshold key infrastructure. But it's a TKI that puts you, the user, in control. You decide who to trust. You decide how much to trust them. And you decide when to stop trusting them. No lock-ins, no proprietary technology that I'm aware of at any stage. I have no patents on it. All the code is MIT licensed. And there is a pre-alpha release now available on GitHub. Getting very close to being able to make a beta release. Obviously with crypto software, I'm a little nervous about releasing this before a lot of people have examined it because, well, you know, you guys hack stuff. So I want some folk kicking the tires on this and telling me what's wrong before I tell other folk to start using it. Okay, so the mesh is a TKI that in theory can provide end-to-end encryption and lots of other stuff for any applications. But it's also, as with any infrastructure, it's a network effect construct. And the problem with network effect is that until you reach critical mass, what we call viral marketing from network effect becomes chicken and egg. And so what I'm focused on at the moment is looking at applications of the mesh that provide early adopter users with real value, even if nobody else ever uses it. So one example of that is an end-to-end secure password vault that's using the threshold cryptography to secure the data in the cloud rather than the dopey, let's encrypt our passwords under another password that dominate today. So we're going to use the cloud to control decryption of the passwords, but the cloud cannot decrypt. And this, and the very first version of that is to address a particular gap in the market, which is a password vault for web service keys that are used inside enterprises where you have that script that has to get to that web service somewhere else in the enterprise and use a username and password to authenticate. And those username and passwords get written into the scripts, and then the scripts get loaded up to GitHub. Oh yes, it happens. If you want an after bit for this talk, load some passwords and some private key files up to a GitHub repo and see just how fast it is before somebody uses them. But the long term, of course, is to be able to secure any type of end-to-end secure messaging and also social media. Wouldn't it be nice if we had the ability to do end-to-end secure Twitter and Facebook type groups in small groups in private? So that's the mathematical mesh. That's why we need a threshold key infrastructure. Here are some additional resources. You can get them all from the website, which is mathmesh.com. But yeah, there's a GitHub repo. All the specifications are out there as internet drafts. And there's a mailing list, mathmesh@itf.org, and videos explaining it all. So please join me. I need help. This is a call for help here, a call for participation. I think that we can do something that could be really special. Let's do it. Thank you. And questions?
You are watching Beyond End to End with Philip Hallam-Baker. Philip, thank you very much for joining us today.
Thank you very much for having me here. It's really great being at Hope, and you know, we're not there in person, but you're getting some of the vibe.
Absolutely. And to continue that vibe, we do invite those of you attending Hope 2020 to ask Philip your questions. Please post your questions to the live stream Q&A channel on our Matrix server, and they will be relayed here. We've had a lot of good discussion going on during your pre-recorded segment, and some interesting questions. One member of the audience asks, how do you ensure that the key generator itself is not compromised? I remember there was an NIST standard for a key generator, which turned out to likely be intentionally flawed.
Okay, yeah. Actually, I think it was an NSA, the dual AC RNG thing. To answer that question, I'm actually planning a mini course on 5 parts on side channel attacks. What you've got there is malicious cryptography, where you're deliberately trying to leak the random number. And so that is a very important consideration. It's not something I can really give you the reason why, but it's something that's been informing the design from the start. And one of the nice things about using Threshold is if you've got your private key has come from 2 separate machines and you join the 2 together, both of those machines have to be compromised in order for your private key that you end up using to be compromised. So it does actually provide you with a layer of protection against precisely that class of attack.
Indeed. We have a fairly straightforward question here from the audience. What if the cloud server gets destroyed?
It's a straightforward question. It's not a straightforward answer. I have been giving a lot of thought throughout the design of the mesh to questions of backup and recovery, while still wanting to avoid government, warrantless recovery. So, or even lawful access, whatever. So the key thing, the first thing is, how can you guarantee that you've got access to your data, even if your cloud service provider goes out of business? Yeah, I've got $2,500 worth of IoT stuff embedded in the walls of my house. I couldn't use it for 2 years because it was all hooked up to a Revolve hub, and Revolve was bought by Google, and they just took them out of business immediately. So yeah, they gave me the money back for the hub, but not for the stuff in the walls. Yeah, I've fixed it since. So yeah, you've got to be able to reclaim your data. And so what you can do is, if you've got one device that has your mesh loaded onto it, you can go to any other mesh service provider and just move your mesh service. And I've got the logic worked out how that works from a cryptographic point of view. There will also have to be some sort of service there that allows you to advertise the change, because one of the things we've got to achieve here is to make sure that the switching cost is low. You've got to be able to move from your Meshco cloud server to some other cloud service provider without it impacting you. You also want to make it so that you can run your own mesh server, and then maybe you decide, well, it's getting too much for me, I'll use an outsourced one, or go the other way. So yes, it's been thought of throughout, but it's not a simple answer, because it's not one answer, it's a whole series of things you've just got to do right.
Indeed. A member of the audience asks, is the background on ECDH any issue with MathMesh vis-a-vis weakdh.org?
This is the logjam attack, and what was going on, that particular attack isn't relevant. And actually, one of the things that pissed me off immensely is the reason that basically this was an attack against TLS. And if you use perfect forward secrecy in TLS, you do it in 2 stages. First of all, you do an RSA exchange, and then you do a Diffie-Hellman exchange on a repeating basis, so that you're always using a fresh key. And when we were discussing that, I said, well, why isn't the key that we're going to use to encrypt the channel, why isn't it a key derivation function of both those sources of keying material, rather than just the ephemeral key? And I was shouted down. And then I discovered why when Snowden launched, one of the things that we discovered was the Bull Run program and $250 million a year being spent to sabotage crypto. So
that particular attack doesn't affect the mesh, and we're using elliptic curve Diffie-Hellman, not just plain Diffie-Hellman. But yes, you have to be careful for that type of issue. And one of the issues with all Diffie-Hellman schemes is if somebody breaks the modulus of the system that you're using, everything will fall apart.
A member of the audience asks about the stovepipe analogy. Aren't you summing up what happened once capitalists got hold of the internet? Everything was RFC protocols before that. I think the last universal protocol to be specified was RSS. It's against the interests of Silicon Valley to allow walled gardens to break down. How do we solve that?
It's against some people's interests in Silicon Valley. When David Chan was giving his keynote address at the first web conference, which was really, I would hope it's recorded somewhere because it's a really powerful address. And what he was railing against was interactive TV, because interactive TV was a big walled garden plot. And there was nothing interactive about it except that if you watched a film, then you could buy the T-shirt. That was the limit of their vision of interactivity. And so I'm very conscious of that. But when we built the web, we actually went out to Microsoft and the rest and begged them to adopt it. You know, we sold Microsoft on the idea of using the web. You know, they didn't steal our stuff. And the thing is that capitalism, yes, if you've got a monopoly, you've got a really bad situation. But the other thing is that although there's the monopolist who's doing really well out of the situation, well, there's all the other capitalists who aren't doing so well. And so the game that you've got to get to is to play one side against the other and to find a coalition whose interests align with yours. And so, I mean, like, we've done how many $1 trillion worth of commerce over the web? That was possible because the web was open. The mesh does the same sort of things, but instead of it being a transactional, ephemeral communication we're securing data in the cloud, we're securing messaging, and doing it in a way that enables strong, end-to-end, joined-up electronic commerce. What's that worth to you? So, yes, it probably will put some technology company nose out of joint, but the key is let's find some technology companies who can be on our side.
Yeah, it reminds me a lot of like the early web era, and you had the big online services at the time, like CompuServe, America Online, Prodigy, who were all very resistant, it seemed, to connecting onto the greater internet and allowing, even allowing email addresses that worked outside their own walled gardens.
Oh, absolutely. Yeah, I mean, like, the folk who are the ogres now, they were the little guys.
Mm-hmm.
You know, I remember when Google was the underdog. I remember when Microsoft was the underdog to IBM.
Okay, another question from the audience. Why would TKI reach critical mass in terms of usage given current use of PGP, knowing these are very different things?
Well, one of the things is that, I have a whole talk about deployment that I've been thinking, if you're going to to change something as big as the internet with 1 billion users, you've absolutely got to design for deployment. Okay, so the first thing you've got to look at is, okay, you've got a user base with PGP. How do we help the PGP community solve its problems and solve the usability problems of PGP? Wouldn't it be nice if I've got a PGP key, but it's only on my desktop? Wouldn't it be nice to have that on my phone really easily? Wouldn't it be nice to be able to join together all my devices so that I can receive my PGP mail on all of them? So the mesh can give you that. It can give you the way to join up all your SSH pieces. And so the idea is you solve a lot of little problems for people, and eventually you get to a critical mass. And this is how we deployed the web. The reason that the web took off at CERN was that all the information at CERN was being hoarded on CERN VM, which was the central IBM mainframe. And CERN was created, I was told by somebody fairly high up in one of the intelligence agencies. He just looked at me and said, well, you know that CERN was created to spy on the nuclear physicists, put them all in one place to make it easy. Well, when you thinking in those terms, CERN VM,
Right.
all the information channeled through them. So if you wanted to telephone somebody on the other side of the campus, you had to go through CERN VM to get to the phone book.
Mm-hmm.
And all the meeting minutes, all the schedules, whatever. And it was a pig to use. So once the web started, you could just go to the web. It was all on your workstation now. And so that's how we got Critical Mash at CERN and so on. So it's all bootstrapping. You've got to have a deployment strategy. You've got to design into that strategy. But yes, I am thinking about that. And that's probably what's taken most of the thought in the mesh, actually. Designing the actual thing itself is the easy part. Deployment, that's the hard. The devil is in the deployment.
Always. We've got just a few minutes left. I see one more question from the audience. Someone asks, are there any theories on how quantum computing will affect key distribution?
Okay, again, I'll just pimp my introduction to crypto course. You can go to mathmesh.com and get a link there. That's an introduction to modern cryptography. I've just finished doing a threshold course, and the follow-on to the threshold course will be either a course on side channel or a course on quantum cryptography. Now, quantum machines exist. Yeah, I've programmed them, but they're not anywhere near close. They're nowhere close to breaking modern crypto systems, in my view. And my perspective here is, I've got a degree in nuclear physics. I did experimental particle physics. So I know the difference between a machine you can run reliably for a year without stopping, which is what you need to do to break some, use Grover's algorithm or whatever on a lot of these keys, and a system that will work, for a few milliseconds for a demo. And in particular, all those machines where they have to get to the super cooled machines that are simulated, that's not a scalable approach. So I think that we're 2-3 decades off having a practical quantum computer. But having said that, I've given a lot of thought into how we can make the mesh quantum resistant. I've not written a lot of that down or done much design work, but I've not been paid for 18 months doing this stuff. If some government research lab wants to pay me, I will write a report that will tell you how to do it quantum resistant. But right now I'm just focused on getting it working with traditional public key cryptography and the threshold techniques that work on public traditional PKI. I'll do quantum at some point in the future.
Indeed. And as we wrap up, one more time, where should people go who are interested in this work and in getting in touch with you?
Okay, you can go to mathmesh.com, and that's got links to, if you go to the documentation tab, that's got links to all the other things. There's a GitHub repo. All the code is MIT licensed. So, you can stick this in your own product if you like. I mean, I'm not going to write a web browser, but my password manager gives you end-to-end threshold secured security. So, grab my password manager and your user's passwords are secure even if the cloud is compromised. So, it's got links to all my talks on YouTube, and all the specs are submitted to as internet drafts. So you can pick those up and you can see details of how it all works.
Excellent. Philip Hallam-Baker, thank you very much for joining us.
Thank you very much for inviting me. Been great.